Here, basically, what we'll be trying to do is focus on optimizing the deployment strategy when first case that Sherif showed basically focused around a 10-year overbuild. We are not doing any augmentation of any sort. This case here, but if you are doing a 20-year, 25-year projects, you are going to be doing some kind of augmentation. And when you are doing augmentation, the question that often comes up is, what should be your augmentation strategy? Are you going to go with AC augmentation or DC augmentation? How often you should do your augmentation? How frequently, what should be your initial overbuild duration? So that kind of question is basically impactful because the amount of augmentation you do, when you do augmentation, how much capacity you add, all this adds to your overall project CapEx and OPEX as well. And that eventually impacts your project IRR. So what we're going to do in this example of this new version, we have added a new feature called the Augmentation Optimizer. So that based on some user input, it basically gives you an optimal augmentation schedule from the program. And in this example, what we'll see that we're going to use that feature. We'll see the results of that feature. We'll have a discussion over that. And we'll see how that feature allows us to optimize our project internal rate of return. Because eventually that's what is most critical. Yes, you're reducing your cost of your projects, but then eventually how does it impact your overall internal rate of returns? So with that background here, what we'll be doing is we're going to be designing a 400 megawatt project in the ERCOT territory. Even though it's the same size as the previous project, the profile that we'll be using is going to be different. The previous project that we ran was a 1 cycle per day standard cycle. In this one, we are going to be using the market signal, right? Because every market is a bit different. There are different services available that the BESS can subscribe to. So we have added a new feature powered by our partners, Horizons and ES Energy, that allows you to import market-specific signals. We're going to utilize that feature to create a market profile, and then we're going to use that profile to design the project and basically optimize the augmentation schedule. So it's a 20-year. I want to make sure folks understand we are not letting it degrade. The goal here is to maintain 400 megawatt hour at POI throughout the 20-year project's life. And the equipment we're using is, in this case, lithium iron phosphate batteries. We're going to use the 280 ampere hour for this example, and then the SMA SCS 3950 up inverters. You can, if you want, iterate over these batteries and inverter models as well. But right now, I want to focus more for this example on the deployment strategy and augmentation. So if you keep the equipment the same, just depending on the augmentation strategy, your project finances kind of varies. Is kind of the focus of this example. So we'll go ahead. If you can follow along, let me make it full screen here. So we'll do a new project. The first thing we come here, similar to the previous project, we have to specify the target energy and power. 20-year project life, we're going to select augmentation here. That's the deployment strategy. And as soon as we select augmentation, you will see that these two parameters become enabled because now the related parameters needs to be inputted. That's required for the augmentation optimizer. On the aux load source, for this example, we're going to do the PS serving from the batteries. So basically, if you switch between these two options, you will see that how the auxiliaries are being fed is changing. If we go to the POI, that basically means the auxiliaries are being fed from the batteries in line with the POI. If you have a separate feed fed from a completely different meter source. We will do a T-type project here. It's a large project in ERCOT. We're going to enable battery degradation and then also the temperature regulated part of the auxiliary. If you select a battery degradation, you have to input an initial state of health. For this case, we are keeping a completely brand new battery, 100%. Then you come to the interval data. This is where we are going to be using this time series option. So this is where we are inputting how this is going to be dispatched. And to get that profile, we'll utilize this new feature called the generate from market signal. So what it does is if you click on that feature, it asks you to input some information about the project that you're trying to build. So first parameter here is about your project capacity, which we are doing a 100 megawatt project. Then it asks you what is the duration of your project. So till now, in this version, you can select 3 different options. So we are selecting a 4-hour battery. Then what you can do is in the select market signal, it allows you to select a typical market signal in that market. So you'll see the versions that you have has ERCOT and the PJM, and we're also adding new market signals all the time. So in my version, you see we have CAISO, MISO, and other market signal as well. So these signals that we're getting here is basically coming from our partner, Horizons Energy, and what they do is based on, they basically predict the optimal dispatch of the battery in that market and give you a representation of, on different years, how a typical battery is going to dispatch in that market. So you can, in this case, we can go ahead and select, let's say we're doing ERCOT, so we're going to select an ERCOT market signal 4-hour. And as soon as you select it, then you can select the year that you want to be the base for your design, right? So this is where you can select that, yeah, I mean, I'm probably on a design for 2027, or if you want to look maybe more into the forward curves into the future, you can select a more later year if you want that to be your best case. Once you have done that, then you go ahead and you input a file name, and you will see that generate POI profile is going to become enabled, and you go ahead and click it, and it will give you a message that POI profile generated successfully, and you'll also see that POI profile being selected here. Previously, there was no POI profile at this location. If you want to take a look at that profile that it created, what you can do is you can come here into the POI profile diagram. So there are different options. So you select the POI profile. So it is going to show you that this is what the POI profile that we picked looks like. So looked like for this signal on the summer and the winter, you're doing more energy arbitrage kind of services, and then basically energy services. And then in the shoulder months, you're doing more of an ancillary services. All right. So once you have selected this profile, your task is done. You have defined that yes, I'm going to build a 100 megawatt 4-hour battery, and this is how I plan this battery is going to operate. So now you go about sizing this project for this. There is one more input that you have to give, which is the TMI3 file. You can come here and you input your TMI3 for Texas. If you want it to be more specific, so what we have already in the library is a typical file in Texas. If you want it specific to your coordinates, project location, you can download that as well from the NREL website. If you give the coordinates, it's going to let you download it for that exact site. Once you have inputted those two, then you go to the equipment tab. This is where you come in and select which battery you plan to use, inverter and enclosure models. So in this case, we said we're going to use the 280 ampere hour. We select that one. Inverter, we'll use the SMA SCS 3950 up. And then on the enclosure model, we're going to use the generic liquid cooled LFP. And these things are completely user dependent, right? So depending on your need, you can select any batteries and inverters that you want to design for. And then if you want to find out the best battery and inverter for your solution, you can iterate over them as well. Then you come to the system specs. So here you see this is blank, so you don't have to do anything yet. And the operational can be blank as well. What you're going to do is you're going to jump to the augmentation. So as you come to the augmentation tab, we will see by default under augmentation schedule type, the augmentation optimizer is selected. So folks who are familiar with our previous version will see that in the previous version, the augmentation schedule type, we only allowed user input. So if you had user input, you had to input an augmentation schedule. With this new version, this augmentation optimizer is a new feature. So if you select that one, what you will see that this is grayed out. And basically, if you run the optimizer, it's going to produce an augmentation schedule and populate it here. So what are these parameters on the augmentation optimizer, right? So let's go over them one by one, and also the objective of the augmentation optimizer. What the augmentation optimizer is doing is based on the project financial information that you have given, it is trying to find the most cost-effective option that basically meets your 400 megawatt hour POI capacity through the 20-year project life and does it in the most cheapest way in terms of net present value. So it combines all of your equipment models and run hundreds of scenarios in the backend and is basically looking for the cost of each of the solution and then eventually suggest you the one that is most cost optimal. So if you come here, first thing you have to input here is the type of augmentation. You can either choose AC augmentation or DC augmentation. So obviously in AC augmentation, you are adding inverters as well as battery blocks. In DC augmentation, you're just only adding battery blocks, so no inverters are being added. Now, to describe all this, what are these parameters and what are these options? So each of the parameters has two options, user-defined and Storlytics optimized. We will refer to the PowerPoint here. Okay. So this will help us to understand what each of these three parameters. So the first parameter is the augmentation interval. So that basically means, if you see on the screen here, what is the duration of your initial overview? The initial system that you're putting in, is it going to take you for 3 years, 5 years, 7 years, 10 years, whatever the years. So whatever you put in here, so in this case, we put in 5. So that basically means that the initial augmentation interval is 5, right? So all the scenarios is going to be looking at, all of them is going to maintain that a 5-year overview for the initial system. The second parameter is number of augmentation. So we get 3. So that basically means all the options it's going to look at is going to maintain the number of augmentations to be 3. So it's not going to look at 2 augmentation, 5 augmentation, 1 augmentation, those scenarios. It's going to look at only number of augmentation to 3. And that's like if you select user defined, right? So that basically giving you some choice to basically outline your preferences. Maybe depending on your project or your team, you might don't want to do less than 3-year overview. So there are things like that you can specify if you want the program to not search everything exhaustively. And then the last parameter, which is the minimal augmentation interval. So that basically means that the minimum duration between 2 augmentation cannot be less than this, right? So in this case, we set 4. So you will see if we are doing an augmentation at year 5, we can do either year 9, 10, 11, but we cannot do at year 8 because this is controlling what is that minimal augmentation interval. Now, for each of these parameters, you have 2 options. So if we go back to our software here, if you select, let's say for the augmentation interval, select the Storlytics optimized, so you will notice that it grayed out that field. So in that scenario, it is not an user input anymore. So the program in the backend is gonna try out different initial augmentation interval. Like I was saying, it's gonna try out 1 year, maybe 2-year, 3-year, 5-year intervals, and then it's gonna look at which is the most cost effective. There are a few different things in interplay here, right? So one thing is that if you're expecting your cost of your batteries to go down, then it might be beneficial for you to not put in a larger battery to begin with. But then you also have to take into account that if you want to do too many augmentations, and we know that for lithium-ion batteries, initially they degrade much faster than the later years. So there are some trade-offs that you are taking in there. So when you combine this degradation impact, the RT impact, along with the cost impact, you start to see that all these different options causes you a significant difference in the overall cost of NPV. So for me to illustrate this fact a little bit more, the question might be, when should I select user defined? When should I select Storlytics optimized, right? If you, let's say, select all these 3 parameter user defined, you're being very prescriptive, right? You are actually narrowing your optimization search space, only looking at handful of scenarios. In this case, we define all these three options user defined. So in the backend, the program looked at 10 different options because there are not a lot of scenarios to look at. It looked at 10 different options and saw that the difference between the most expensive option and the least expensive option in terms of the augmentation schedule around 1%. But if you make some of these parameters Storlytics optimized, so we made two of the parameters with the augmentation interval, Storlytics optimized, and number of augmentation also is optimized. Now the program in the backend is not just looking at 3 augmentation schedule, it is looking at 1, 2, 3, 4, 5, and others, as well as on the augmentation interval, that initial overbill, it is looking at different combination as well. So here you can see that in this case, it looked at 58 different combination, and it came out to be the one that is most cost effective is like 93%. So there's a 7% improvement, like difference between the least cost option and the most expensive option. And basically an insight that I want you all to take from here is what happens based on this. If you can set everything to Storlytics optimized, and that basically means that you are running a lot of different scenarios and it's going to take you some time. Or if you can reduce the search space, be more prescriptive, that's going to cost you less time. But the possibility there is that you might miss out the most optimal solution. So here I had one more example here where we are running like almost 96 scenarios. And you can see that between the least expensive and the most expensive, the difference is almost 14.5%. And all this depends very much on the equipment you select, its performance, but also some of the cost assumptions that you are inputting. So once you go ahead and basically you run the augmentation optimizer, what it is going to do is from that it takes some time to run it, and basically it's going to start running. And it's going to take some time, right? So I'm actually not going to run it. I already basically pre-ran it and generated the augmentation schedule. So in the essence of time, we can load that example case and we'll proceed from there. But essentially what this is going to do is once it's done running, it's going to input that augmentation schedule here, and then you'll be able to run the project and basically see the other parameters. And once it's done running, it's also going to finish up there's this show results button is going to become enabled, and you will be able to see that the augmentation schedule that you are getting is that like really optimal. So one of the graphs that you're going to be getting is this one. This is one graph. So that tells you that how much of a cost differential you're getting for the optimal solution. Second graph you're going to get is that, because one thing you wanna really maintain that all this augmentation you're doing, your eventual goal is to maintain that 400 megawatt hour, right? And you can see here that the optimal one that it's proposing is saying that your first augmentation interval should be for 3 years, then you come into another one in 7 years, and then do another one in 12. And you are able to maintain your POI capacity, right? So that gives you the confidence that, okay, yeah, we got an augmentation schedule that maintains my capacity. And then the last thing the augmentation optimizer will give you the state of health. A lot of times what happens nowadays in the calculation or kind of the practice is you get a one generic degradation state of health profile, and you basically apply that for all of your augmentation schedules. So you basically apply the same state of health degradation for all the augmentation schedule. But in reality, that's really not the case. Each of these augmentation phase is going to have their own degradation. So here for the optimized run, it gives you the state of health for each of the individuals run. So you have your initial build, which is the blue one. Then at year 3, you add a new battery through augmentation. This one is giving you the degradation for that phase 1 battery, and then phase 2 and phase 3, so on. So the impact of adding augmentation on degradation is really taken into account in the augmentation optimizer. What happens is that you get an initial augmentation or state of health prediction based on your uses. But as you add more batteries, your initial system is not performing the same way. It is having to do less, right? Because now you have had more inverters and maybe more batteries. So the burden on the initial system decreases, and that's going to cause it to degrade less. So that interplay with augmentation and degradation is captured through the augmentation optimizer. Then the next step for us is we're going to go ahead and load that profile, because it does take some time to completely finish. So if you go under File and go to Open, we will open the example ERCOT BESS underscore AC. So that's the AC augmentation solution. Just double click on that one, and it's going to load that project for you here. So we are basically just picking up from the output of the augmentation optimizer. So once the augmentation optimizer is done running, it basically generates that augmentation schedule. And then what we're going to be doing is we're going to be coming to the financial, and we're going to be inputting some of our revenue options. So for the revenue, we have two different contract types that is allowed now. One is a tolling agreement and one is a margin market. So in the tolling agreement, you select when you do place in service contract terms, and then there are some tolling agreement related performance matrices. So you can choose whether to include all of these or you want to do one or another. So first matrix is regarding the energy capacity. So most of the tolling agreement is going to have some kind of LDs associated with if you fall short of your contractual capacity. So what it does is, if you have this feature on, it looks at what is your year-over-year capacity, it compares it with your target capacity, and if you are falling short, it is calculating a penalty for falling short. Same for your RTE. So we have had it set at 88%. And once you simulate the project, if the project RTE is below this, and it's going to go down with time, your RTE LD is going to keep increasing. And then the availability factor is also in there. So you can specify what's your guaranteed LTE availability, and then what are the availability you're getting from your suppliers. So you can take the impact of availability in your revenue penalty calculation as well. So what really it does is basically it allows you to connect your system performance with revenue. So if your system is underperforming in terms of capacity, in terms of RTE, now with the feature help of this, you'll be able to see the impact of that on your potential LDs and the revenue that you are going to be making. Now, these things are coupled with some of the parameters under the financial model. So if you come into the financial model, there is a cost piece, but then there is a revenue piece too. So in the revenue piece, in the tolling agreement, this is where you can input your fixed price for your tolling agreement in $ per kW month. And you also get to set some of the rates for these LDs. So all these are customizable, and you can set it depending on your project and your financial models. So you do that for the tolling agreement, and you have a separate for merchant market, which I'll cover later when we're doing a merchant market example. As soon as like this is done, you just can go ahead and run it. Now for the augmentation, once this run is done, you can click the generate report button to generate the report. So I have the report pulled up here. So in the report, initial segment goes over the power and energy adequacy. So you can see in terms of power, we are meeting the requirement. In terms of energy, we are meeting it almost 97.5% of the time. So that's pretty good up there. And then what we do is we go into the system efficiency. So one thing I want to point out that's new in this new version, we added the option for cycle RTE as well. So now you see two RTE reported. One is a simulation RTE, another one is a cycle RTE. So the difference between the simulation RTE and the cycle RTE is simulation RTE is based on your dispatch profile. So in the dispatch profile, like you can already observe that there are cycling, but then there are idle time as well. So even when your system is idle, it is providing for your auxiliaries and other things. So the simulation RTE accounts for that. And on the cycle RTE, it doesn't look at idle time. It's just a typical a full cycle RT where you charge the battery from minimum to maximum and discharge it from maximum to minimum, and it calculates the RT based on that. So that's one factor. We have the losses. So this was in Texas. Summer months were consuming more auxiliary losses here. And then we had the throughputs and others. So I'm going to jump to the main part here. So the main thing we wanted to check was that are we meeting our POI requirement? So which we see we are meeting our POI requirement. So once that's verified, we jump to our next section, which is basically the cost. So in the cost segment, you will see that there are different components to the cost. So there are a couple of new components that have been added from last time. So we have the GSU and the high voltage breaker cost added. So if you are doing a T-type project, there is an input for these two parameters in the financial model, and based on that and the size of your project, those costs are going to be accounted for. And you also have a balance of plant cost to account for your EPC cost. So now really the cost that you get from the software is really the overall project cost, which pretty much takes everything related to project into account. Then it gives you the breakdown of your OPEX. So this is an interesting chart. So year over year, I think Sherif also mentioned that is the OPEX going up with time. So escalation. So you kind of see that the OPEX is escalating over year. There are 4 different components. The light blue here is the energy loss. So that's the part basically is your auxiliary consumptions. The second part is the state of health guarantee. Other terms for that is performance guarantees and LTSs and preventative maintenance. So what this is showing is that first 3 years, you didn't have any state of health guarantees, mainly because in the file that we utilized here, if you go here, you will see that the standard warranty terms are 3 years. So first 3 years already covered. So there was no extra you had to pay for the state of health guarantee. After that, when you're going for long-term performance guarantees, you're having to pay for it, and that price is taken into account. And then you also have here, we did 3 augmentations. So 3, 7, 12. You can see the breakdown of different components of your augmentation. So your cost of your battery, which is the green one. We did PCS, because this was AC augmentation, we added inverters as well. So that's the orange one. And then on top of that, there are some plant integration and other costs related to augmentation, which is the gray one here. So it really gives you a good breakdown of your OPEX and how the operational cost varies over the years. Then it takes you to your revenue. We are doing a tolling agreement, so it's a fixed revenue, not changing. But on the negative axis here, what you see is the different LDs. So one of the things right away is that our availability LD, because we set our target to 97 and then the actual availability is 94. So it is a straightforward calculation there. And then on the RTE LD, if you look at our target was 88%, and what we get here to begin with is around 85.48%, right? So with time, it's going to go down. So we are falling short of 88 at the initial years, and then with time, it's just increasing. So you'll see that the impact of that LD is here in the revenue chart as well. If you focus on that light blue one, it grows with time. Once you got your revenue, you got your complete project cost. Now it's about looking into the cash flow. So in this case here, it is giving you the initial CapEx. We have included ITCs to be applied at year 0. So it's adding that. Also a 5-year maker's depreciation, along with the green one here is showing you every year net revenue, basically. So the years where you had to do augmentation, you will see that net revenue pretty low. And with that, it gives us a unlevered IRR of 9.5%. So one thing to clarify, the IRR reported here is before any kind of debt finance, debt equity, other kind of financing. It's just the levered IRR of the system, which takes a cost, ITC, depreciation, and revenue. And then there is another chart that gives you, if you're looking for your payback period, which is by specifying a certain discount rate. So if we apply a 5% discount rate, the payback period is going to be 13 years. Okay, so I think that covers the base case for the AC augmentation. So we ran the augmentation optimizer, we got an augmentation schedule, We ran that augmentation schedule and we got an unlevered IRR of 9.5%. Yes. So we have a guaranteed LT of 97%, and the actual availability is also a user input in this case. So we said the actual availability is 94, and that falls below the 97. So that's what triggered that availability LT. Right now, this is not something calculated from the program, that availability, because that's very much dependent on maintenance and the quality of the product that's being supplied. But a lot of our users wanted to see the impact of that in the revenue stack. So we made it an input. So typically, if you're contracting with Sungrow, Teslas, and others, they are giving you a contractual LD, like a availability percentage, and then you are signing up a PPA with a certain guaranteed availability. So you can input this number based on what your suppliers are giving. So here I had it set low, just to show that point that your availability LD gets triggered if you have a lower value. All right, so with that, let's just go to the next case. So we covered all this. So the next step for us is to do a DC augmentation, right? So we ran an AC augmentation, we got the optimal stuffs, we got our final results. Now we're going to switch to a DC augmentation. So all you need to do basically is come here and make it to DC, run the augmentation optimizer. It's going to generate a schedule for you, and then you're going to do run. Since some folks might not have access to the optimizer, we give you the project file. So if you open the project, which is ERCOT example BESS _ DC. So that's DC augmentation. Open that one. So I already pre-ran, populated that one. While it runs, I have the report up. This was the DC. The DC augmentation, after it runs as well, is going to show that it maintains the capacity, even though the initial overbuild and the number of overbuild are similar to AC, but when the augmentation was done is a bit different. So in case of AC, the first augmentation was done year 7, and I think then year 13 or 12. In this case, for the DC, because the way the system is executed during DC is different than, and you have less inverter, less losses, that causes your degradation to be different, and that causes a couple of years of shift in your optimal profile. So we run that one, and then let's go back to the PowerPoint here, where we have some observations to share based on this. So first observation is that, so what we are showing is that the fact that I was talking about is about the degradation, that if you would not have like done augmentation and you don't take the impact of augmentation on degradation, you might be, like overestimating degradation, right? So to showcase that point, what I have on the screen here is you have this red one. So red one is you didn't do any augmentation. You had that system, you just ran it, let it degrade. So no augmentation is done. So that's what gave you that red one. And then this green one and the blue one are our AC and DC augmentation. So what you will see here is that at year 3, up until year 3, all of them were on top of one another. At around year 3, now that you added more battery, now your initial system needs to do less. That means it's going to degrade less, right? The C rate is less, the depth of discharge is less. So now it is having to do less. So you see that from year 3 onwards, that your degradation starts to decrease. So for the AC and DC augmentation case, the degradation rate slows down as you are adding more and more batteries and inverters. And you can see up until year 20, it's not as less. It's like almost 3 to 4% difference compared to your initial system. So now what the detailed nuance here is typically when you are designing it, you are getting that grade 1 from the provider or the OEM's one state of health curve, and then you are basically applying that for all of your different degradation steps. And that's going to lead up to you with a more conservative system which can be 3 to 4% off than what it actually should be. So that's one factor, and that's very critical that of this whole. So then the second observation of the augmentation schedule, we kind of touched a little bit on there, that the AC augmentation and DC augmentation, they are not adding capacity and same amount of capacity in the same years. So you'll see that AC augmentation at year 3 added, but didn't add it as much as DC augmentation needed to do. And then at year 7, AC augmentation was doing phase 2, but for DC augmentation, that was year 8. And then here, year 12 versus year 14. So really, because depending on the solution it is running in the backend and the interplay of those complex dynamics, it is determining that what is best for what configuration. We covered the RTE part in detail, so I'll skip that. That comes to our cost of ownership. So we saw that compared to the AC, the DC augmentation was around 1.2% cheaper because you needed similar amount of battery configuration. For this example, you needed a similar amount of DC battery to be added, but on the AC augmentation, you had those extra inverter cost that was not there for the DC. So the DC came out to be more cost effective. And then when you take that and look at the impact of that on your IRR, that gives you 9.7% compared to AC giving you 9.5. So yeah, for this project, for this setup, with the set of assumptions that we have, we're going to go with the augmentation to maximize our IRR. And then the last case I had was just to show that, how you can utilize this to compare different market structure. We already ran a tolling agreement, and then I went ahead and ran a merchant market with the numbers. And really what the merchant market shows that the revenue are not as much. You are actually not going to be making any profit. The IRR is like negative 1.4. So for this structure, with the inputs that we had, is basically telling that this merchant market option is not going to be economically viable. Right. So when you are looking at different contract types or trying to set pricing for different type of contracts, you can utilize this tool to understand where those prices needs to be for you to hit your target IRR. So with that, I think that wraps up that case.